All right, for every action, there's an equal and opposite reaction. We all know this, right? If I take away the action of gravity, what is my body's reaction? Huh? Surprise! Big surprise. Yeah, anyone else? What types of surprises? The major, right? The one major reaction we take away gravity force is our body's fluids. They start to shift because they're no longer being pulled to the bottom of your feet. It starts to shift. Okay, so like medicine, you take a pill and it fixes one thing and then you get a bunch of side effects, yeah? Yeah, I usually try not to read those. They're scary. Okay, well, what does this one side effect, what this one pill have? What are all the side effects? The fluid starts to shift, but now I have side effects of my heart doesn't have to pump that hard anymore. I start to adapt to my new environment. Humans are incredible. Our ability to adapt is unreal. So my heart says, well, I don't have to pump that hard. Get down to the bottom of my feet. My pressure's even. I'm going to go smaller. I'm going to atrophy. I'm no longer walking and running on my feet. I'm just floating around. So now my legs are like, well, I have to carry this load. So it gets smaller. Okay, no problem. I don't need it. So what's the issue? Okay, what else is a side effect? Well, my eyes, my organs, now my eyes, they start to feel this unfamiliar pressure behind them. And they start to distort. That's going to be an issue, right? Lots of these things start happening. And it doesn't really matter that they happen because I'm in a new environment. It only matters when I come home. So if you plan to stay on the ISS, no big deal. Good job. You're going to look like a bird. You're going to have like little teeny legs and big face. It'll be fine. But if you plan to come home, you might have an issue. So let's talk about those issues a little bit more and then find a way to solve that. Because if I go to the ISS is an accelerated test bed. We're there to do experiments, not ourselves all the time, right? So, okay, let's figure out what ourselves are doing and fix it so then I can do a real experiment, right? Not ruin my life. So, we learned a lot by these two twins. Have you guys heard of them? Yeah? We have Scott and Mark. Scott went up to Leo, low Earth orbit, or on the ISS. He spent a year up there. Bless him. He came home, though, kind of looking a little better than his twin, if you ask me. He's got a nice full face, a little taller, and so things out. But he also did have some more effects, okay? He did atrophy. He was more puffy up top, but he did atrophy, okay? So we can have, in 2 weeks, you can lose up to about 20% of your muscle, and then in 6 months, you lose like 40% of the strength of that. That actually does become an issue because now you might not be strong enough to do the task that you were trained to do here on Earth. So it might become an issue, and then God forbid something goes wrong and you're supposed to lift something and now you can't, right? Because you only have 60% left of that muscle. And then also to consider before we move on, atrophy. It happens, like I said earlier, the ISS is an accelerated test bed. What do I mean by that? It means everything that happens up there happens here just really, really fast. So if I can understand atrophy within 2 weeks, you guys can put a cast on your leg. It's like, what do you like? Oh, so you start cast on 18 years old. Okay, so you still have hard cast. You take the hard cast off. You got a really, really skinny leg. And then the other leg is not skinny. It took you how many, what were you in that? Your cast for 4 weeks? Okay. You 4 weeks and you already see a little bit of a difference, right? You see more of a difference in 2 weeks. So maybe we can learn something and apply it here. Okay, you're going to see that in kind of all this stuff. I'm not going to go too much into the bone because our next talk is going to be all about bones. So she'll go really into that. But we do know that to prevent bone loss, the best way to do it is to apply force to it. Is there any engineers? Half of us are engineers. Okay, so do we know when you apply a force, you want the whole force and not like a cosine or sine of a force? Yeah, you want the whole force. So when you're thinking about doing countermeasures, you want to think about how do I get the force vector to be completely on that bone? So say this is my leg, I want my force vector to be all the way perpendicular to that, right? I don't want it to go at an angle. Keep that in mind when we go to design a machine later on. Everyone's going to design a machine. Okay, so some bad things happen. Our body says, I don't have to carry you anymore. I don't have to be as strong. And some things happen with our bone remodeling cycle. And like I said, I'm going to leave that up to our next speaker to go in depth. But staying kind of on the surface, osteoporosis does occur. Okay, it occurs super fast on the ISS, but it takes up to 3 to 4 years to get back here on Earth. Okay, for our cycles to resync. All right, so it is an issue, and especially on landing. When you land, the risk of you breaking that bone, it's like your grandma falling. That's really good. That's not good. Okay, so if you want me to land, and now I'm landing us in the ocean in a little floating blob thing, and now I'm like, I'm gonna break a bone. Okay, so that's a solution, something we gotta think about. It also affects our eye. I said that we're not used to the pressure behind our eyes. It pushes out. The same thing happens here on Earth, glaucoma. Okay, except for it takes a really long time to get the glaucoma in a lot of cases. But up in space, we're seeing that people are starting to get nerve damage. And it's because that fluid isn't being drained. It's now staying up there. There's no gravity pulling it back down, so it's staying there. That can cause serious eye issues. Okay, so glaucoma, it can change your vision. The twin astronauts, the guy who came back, he now wears glasses. Sometimes it's not good. And they're starting to see that there might be a difference between men and women. Now, I'll get into that study a little bit later, but we'll see if is it really like a sex difference with hormones, or is it a difference because there's more male astronauts, so they just see it more? I don't know. Let's do some research. Here are some pictures of what your eye kind of looks like through different phases. So here on the first picture, you have your no big deal, the early microgravity, and you have that fluid buildup. Now your body is going to adapt. As I said, we adapt really well. So in that environment, we say, okay, to make some room, we're going to adapt by changing our volume structure. And again, that doesn't really bother us there, but it is a problem when we come back. So now I'm landing, and now I'm having eye issues. So how am I going to get out of the little blob thingy? Maybe now I can't see. Oh my God, it's issues. And those are issues we have to think about. So now I ask myself, okay, well, what are they doing about it? If we know all this bad stuff is happening, why aren't they going to fix it? Well, they do have 3 machines up there. I don't know what they're doing, but they're not fixing it. Right? I mean, they're not. Half the time they're broken. So, sorry, Nelson. But, so if we look up at these, we have the A-red at the very furthest one. What do you think the A-red's for? So far, if you've kept track, I've talked about muscle atrophy, bone loss, and some cardiovascular issues. What's the A-red supposed to defeat? Some muscles. It's some muscles, right? It's the A-red is muscles. It's like a Smith machine. Think of the Smith machine. You're really working the muscles. Okay, what is the little cycle machine supposed to do? Cardiovascular, very good. And then lastly, what is the treadmill supposed to do? Bones, very good, bones. Because when we're running, and they do this 2.5 hours a day, by the way, all 3 of these, and they still come home a wreck. It's not really good. So if we look on Earth, if we see the black mark, that's our bodies, the impact that we feel. Remember, with bone loss, to get rid of it, we have to feel impact. We have to load our bones in order for them to keep going through their normal cycle. If we unload, they're not going to do it. They're going to say, I don't have to, so why do it? Okay? So this running device that they have, they threw up a treadmill in space, which, by the way, the treadmill's really heavy and really big. And they put these little bungee things on, okay? So the black mark is what we feel our impact on Earth. It's about 2 times our body weight. Then the largest strap, which is the red strap that goes down, is close, but it's not as, it's not there, right? And then the colors go down. Well, P.S., they can't use the red, and what color is that? Blue? Red and blue, because it's so tight, it hurts the astronauts. They can't run because of the amount of resistance that's pushing down. So really, they can't even get the effect out of this. Okay? So there's a big question of what's a better countermeasure? What can we do to maybe make one machine instead of 3 and maybe make one that actually works? That would be great. What is the main reason that these 3 aren't working? What's missing? Gravity, yeah. All 3, you saw my whole sheet, didn't you? It's alright, I gave it. No, in all reality, right? The ARED offers one form of resistance. The cycle machine offers one form of resistance, and so does the treadmill. On Earth, you naturally get 2. You get the resistance of the machine, but then you also have gravity. So you have to start thinking about, okay, I don't want to only get 2 times my body weight when running. I need to get 2 times my body weight with the gravity, okay? So how do we go about that? For my, I think this is my thesis, I moved to Brazil for like a year, and this chunk of junk in front of me turned into a patent, so don't laugh, okay? Don't laugh when I show you that. It's genius. I thought, okay, I need to work on muscles, bones, cardio. First thing, go to the gym, so I kind of know a little bit about muscles, thought I'd hit that first. I know to be efficient, the area underneath that curve is my work. If I go to space, I don't want to work out for 2.5 hours. I want to look out the windows and do experiments, okay? So I want to be efficient. The red line on the resistance curve, if I just kept it a constant. The blue line is a varying resistance. I know if I can match my varying resistance of my machine with the human strength curve, I'm golden, okay? Human strength curve, does anyone know what the human strength curve is? If you do a chest press, am I stronger here or here? I'm stronger here, right? And I become weaker here. So if I build a machine, I want it to be kind of easier, and then I want it to get kind of harder and harder and harder and harder. And then I want it to go the opposite way. So if I can match, if I'm working my chest, if I can match the resistance curve on the exercise machine with my body part, now I'm being efficient, okay? So microgravity, what do you think? Do I really care about my chest? Do I walk around with my chest a lot? Is it going to actually be that quick on the ISS? No. I'm going to walk around with my chest all day. I don't walk around with my arms all day. So the body parts that are mostly going to be affected in space are going to be the L4 and down. My lower back and down. That's really what's going to affect it. So now I'm going to say, well, I don't really care about my upper part that much, okay? So I'm going to focus on building a machine that focuses on my lower half. So I'm going to start looking at the strength curve of my lower half. Well, happens to be, if you look at these two, if you look at a leg press, it's the same as a chest press. I'm weak here, I'm strong here, okay? So build some sort of device that is not so hard here, kind of hard there. Seems pretty easy. Okay, well that takes care of one thing. What about the other 2 problems? That's definitely only massage. What about my engineering students? What about muscle, bone density? What do I have to make sure in my leg press? What do I have to make sure happens? That force vector stays perpendicular the entire stroke. So that means that I have to make a foot pedal somehow stay in the position that it's supposed to stay into. Okay, so I gotta think about that. So I have to calculate how much force am I gonna get out of this thing. Okay? And now I have to think about, well, if I go up, and then Amber goes up, and then Casey goes up, and they're all using my machine. I mean, we're all super athletes, so probably we won't hit this high setting, but, then maybe some guy comes behind us and we have to lower it. But if we have to change the resistance, how can we do that? We have to think it has to be subject-specific in some kind of way. So I said, okay, well, let me do some engineering. This is like basic dynamics, a little, I don't even know if that's advanced. I can call it advanced and I feel better about myself after Amber's talk. But I think it's pretty basic. So for-loop closure, did you guys learn for-loop closure in engineering dynamics?
I'm electric.
Is anyone critical? Alright, well that's okay. So we use for-loop closure. And this is the four, if you look at it, it's really just 4-bar linkage, just a parallelogram. Benefit of using a parallelogram is that it stays parallel. So that means that the force factor doesn't change much. So if I take this and I push it and it goes against the cycle is only going to go about this. What's the benefit of it going back and forth? What was the third thing that was wrong? Your cardiovascular. So now you're going back and forth and back and forth. Okay, so now we have to put resistance on this thing. If you put a compression spring between here and here, what happens when I start here? Is the spring all the way out or compressed? It's all the way out. So that means that it's super easy at this point. But as I push my leg to match my human strength curve, the spring gets harder and harder and harder and harder and harder and harder and then goes back. Okay, if you change the angle of the spring, your starting point is going to be like a preload. So if I'm on my Smith machine or on my leg press machine, I can preload it first. So I think, correct me if I'm wrong, I think the Smith machine is anywhere between like 20 and 45 pounds of resistance. Okay, you can change the resistance on that machine to boost it up. So it's basically taking this curve, instead of setting to 0 on the blue line, you can preset it and it bounces up. You can set it like 40, right? And then you get even more work, okay? So that's good. And now you want to say, well, to really be beneficial, to get that 2.5 hours really down, I want to make sure that, yes, my parallelogram, it's staying that perpendicular force, but now how do I know that my participant isn't going to be foolish and use his toes or his feet or, and then what happens if they aren't going fast enough or if they aren't trying hard enough? What do I have to add in on that? Well, that's where heart rate comes in and different type of biomarkers, your VO2, things like that. And if you put in a pressure sensor on the foot pad, that's kind of up in the corner there. Has anyone played the balance speed game? It's like, woo, it turns like different colors. Yeah. Okay, you have to be like really super awesome and like get all the colors the way they're supposed to be. You have to do that on here too. So it's going to tell you you're pushing too much with your toes or your ankle. That force vector is not being used correctly. So it'll tell you, and it will also change the angle of attack here. This angle, I don't know if this works, but the angle of the spring, it'll change that for you. It'll say you're being lazy, and it'll make it harder, or it'll tell you go faster. Okay. So there's different things to look at. So the reason that we're interested in all of this research on it is we gotta come up with a countermeasure so that our astronauts can go up and do something else, right? That's one of the test subjects in Brazil, or the final product in Brazil. Doesn't look like it's space flight ready, but I did a lot of dumpster diving for those parts. Not proud. They did not have a machine shop readily available like we have here, so we did what we could and it worked really well. So now, I started thinking, okay, I have the mechanical part of it, but we still are missing the fluid part of it. We're still missing the second part of the resistance. So when I got to Grenoble, I said, hey, I want a fancy lower body negative pressure chamber. What is lower body negative pressure? It's gravity. It's a gigantic vacuum cleaner. When you were a kid, did you put the vacuum cleaner on your skin and did it like suck on it or like suck up your Legos and stuff? Yeah, that's what this does. And it just acts like gravity. That's it. Okay? So it's going to first simulate gravity. You go at a certain tilt. Whoop, you're in gravity. Congratulations, you're an astronaut. And then it's going to say, okay, all these bad things happen to you. Let's turn the machine on and get rid of all those bad things. So I put a bunch of my students in here and said, hey guys, just chill out for like an hour. Like listen to a podcast or something, okay? I'm just going to put you in microgravity and go to sleep. One student starts snoring. So they go to sleep for like an hour. And then during that time, and I'll show you some of the results here, I wanted to see, is there a correlation between vital signs, eye pressure? Are there anything that we can understand? Because I know, we know that when you go to space, your eye pressure increases. We get that. But carrying a device, have you been to an eye doctor and they do that weird puff in your eye? The machine's huge. It's awfully annoying. We can't bring it to space, right? So I can't be like, tell me your eye pressure in space all the time. So I wanted to see, is there an easier way to indicate if your eye pressure is raising? Is your heart rate synced to that? Is your blood pressure synced to that? Is there anything we can do? So our first study was just look at the vital signs. Is there any trend with your eye pressure, right? Your IOP. And we found that your blood pressure doesn't do much. Doesn't really change much. Your heart rate, though, your heart rate went way down, like we suspected in the microgravity environment. And then we turned that thing on and it went up. So that was interesting. Okay. Then we also found that it say kind of the same trends with the IOP. So we got a little bit of information from that. And we said, you know what, let's go a little further. Then I got this device. So then I said, okay, well, why don't we get more patients in, and why don't we do a little bit more research on this eye issue? Is it really a man versus woman thing, or just not enough women die? And, well, from what I found, women rock. You rock. No, so we did this. Does anyone know what a tonometer is? Instead of going to your doctor and going, and your head comes back, just put a little drop of numbing in your eye. That's me. That's my husband who is doing the machine. We're both trained on this. But all of this information, I asked myself, how do we get a better telemetry? How can we quantify, if I put this, I pay out, millions of dollars and I get this to the ISS, how do I say it's going to work? I know we have mouse models. I know we have pig models. Where are the human models? I'm not a pig. Yes, I know we're a lot alike. My coworkers might come eat me up. But how do we do that? So we have to start thinking, okay, well, how do we represent a muscle? How do we represent a tendon? The Hill-type model is a 3-element model. Does anyone know what the Hill-type model is? One person? Okay. All right, so we're going to represent the muscle using 2 elements. A contractile element, it's going to represent, the myosin and the actin and the sliding filament theory and all that stuff. It's like why your muscles contract. The spring alongside of it is going to be the plastic around it. I always say it's like a sausage, that weird, nasty white stuff that encompasses a sausage. Yeah, that spring represents that sausage thing. Yep. And then the spring that's kind of at an angle to it, that's your tendon. Now, scientists, this was built way back when. This thing needs to be updated. This is like a gazillion years old. If you look at the contractile element, you're going to have 2 graphs that are associated with it. One that represents the active elements. You have the myosin and the actin and the sliding filaments and the velocity, right? Because muscle acts differently when it's under load, when it's going fast versus slow. You're not going to move really, really fast carrying a heavy weight, right? So those represent that. We can embed that into the code. We can also embed into the code the stress strain of tendon. Does anyone see in those graphs that this model is built around any kind of environment, any kind of extrinsic hazards, any kind of factors? No. You can't happen. No. It's not real time. Doesn't make sense. And even if you aren't a fan of space and you're a fan of rehab or sports, your participant is changing real time. Your models should be able to change real time. They should say, I should be able to say, my participant